Welcome. In this lecture we will return to the operating range of the combustion engine powertrain and then analyze what vehicle performance can be expected for a small car. This analysis will be made for a small car with these parameter values. This is, by the way, the same vehicle as we analyzed in a previous lecture on vehicle requirements, and we assume the vehicle shall meet the same performance requirements. We also assume the powertrain to have the same 5-speed manual gearbox and the same 100 kilowatt combustion engine powertrain we have analyzed earlier. This analysis will be based on the total operating range of a combustion engine powertrain. It has been derived from the engine operating range and the transmission model. In this lecture, we will not discuss which gear is needed in different driving situations. We will just consider the total operating range. Here is the total operating range. We will now plot the required force speed operating points for a few driving situations to see if they fall within the operating range of the powertrain. If they do, the powertrain is sufficiently strong for the required driving situations. This is the running resistance curve for a flat road with the top speed operating point. It can be seen that this requirement is within the capability of this powertrain, since the operating point is within, or as in this case, on the border of the gray operating range of the powertrain. On a 10% gradient, the vehicle shall be able to drive at least 100 km per hour at constant speed, which is well within the capability of the powertrain. On 20% gradient, the top speed must be at least 50. Again, this is within the capability. Now we turn to the short time acceleration requirements. 4 meters per second square at low speed, as well as 4 meters per second square at 50 km per hour are both met by this powertrain. The requirement of 2.5 meters per second square at 100 km per hour is very close to the limit for this powertrain, but still within the operating range. And finally, 1 meter per second square at 150 is also within the operating range of the powertrain. So the conclusion is that this powertrain can meet all the requirements. The top speed on gradients will be possible to exceed significantly, while the acceleration requirements are more close to the actual limit of the powertrain. In quick accelerations, the driver usually will press the accelerator pedal fully and then the powertrain will deliver its maximum traction force. Therefore, it's interesting to also calculate what is the maximum acceleration the vehicle can get at different speeds. Here you will see how to determine the possible performance for the vehicle and powertrain in our example. First, we plot the running resistance curve on a flat road for the vehicle. If we want to estimate the possible maximum performance at, say, 50 km per hour, we read the peak force of the powertrain, which is 6,760 Newton. From that we subtract the running resistance, which is 195 Newton. The difference is 6,565 Newton, and it can be used to accelerate the vehicle and/or drive up gradients. By dividing the force difference with the vehicle weight, 1,200 kilos, we get the normalized force value, 5.5 Newton per kilogram, which is sufficient to accelerate 5.5 meters per second square. This force is also sufficient to instead climb a 20% gradient and still be able to accelerate 3.5 meters per second square. Notice that when we do this analysis, we overestimate the acceleration performance slightly, since we do not consider that some of the engine torque will be required to accelerate the inertia of the engine, transmission and wheels, before it can produce force at the wheels. If more accurate performance values are needed, the analysis needs to include inertia in the transmission and engine. As can be seen, the force at 50 km per hour is close to a peak in the force operating range. When the vehicle is accelerating to speeds higher than 50, the force will quickly be reduced. At about 70 km per hour, the driver needs to change from first gear to the second gear, which leads to a step down in force. At 75 km per hour, there is a local minimum value of the traction force, so it can be good to know what performance is possible at that speed. The peak force is now 3,900 Newton. The running resistance is 290 Newton, leading to a force available for accelerating the vehicle of 3,610 Newton or 3.0 Newton per kilogram. At this speed, the maximum acceleration is reduced to 3 meters per second square, or for example 2 meters per second square on a 10% uphill gradient. This is still fairly good performance. When the speed is increased even further, the maximum force of the powertrain is reduced and at the same time the running resistance is increased. Therefore, the acceleration at high speed is very low. As an example, we can analyze the acceleration capability at 190 km per hour, at which the maximum traction force is 1825 Newton and the running resistance is 1230 Newton. The maximum net force is 595 Newton or 0.5 Newton per kilogram, leading to a maximum acceleration of only 0.5 meters per second square. Note that this is less than 1/10 of the maximum acceleration at 50 km per hour. With this performance, it will take about 6 seconds to accelerate the relatively small speed range from 190 to the top speed of 200. The maximum force also shows that the maximum gradient at which the vehicle can keep 190 km per hour is 5%. This is, however, a very steep gradient for high-speed motorways. All the performance values we have calculated here assume that the peak force of the powertrain is used. To get the vehicle to perform like this, the driver has to select the right gear. If the gearbox is in the wrong gear, so to speak, the performance is lower than what we have found here. In this lecture, we have shown how the force-speed operating range of a powertrain can be used in two ways to analyze the vehicle performance. Either it's used to check if the powertrain can meet the vehicle requirements by testing if the operating points of the requirements fall within the operating range of the powertrain, or it can be used to determine the maximum performance possible by determining the available force for acceleration and gradients, and then use the vehicle model to determine the performance. Now, take the opportunity to test what you have learned about performance analysis using the force-speed operating range of the powertrain by doing the exercises following this lecture.